The molten heart of the earth does not sleep. Beneath the brittle surface of continents and the dark weight of oceans, a vast ocean of metal churns slowly endlessly in a chamber neither solid nor entirely liquid. This is the outer core, composed primarily of iron and nickel, restless, superheated, and moving in immense convective cycles. Here in the depths beyond sight and silence, the first whispers of a magnetic field are born. They do not arrive all at once, but emerge gradually like breath condensing on ancient glass. The heat that drives this motion is primordial, some of it left over from Earth's violent birth, some radiating steadily from the decay of heavy elements like uranium and thorium long entombed in the planet's interior. As lighter, hotter material rises and cooler fluid sinks in slow spirals, the charged particles within begin to drift, and that drift gives rise to a subtle but profound force magnetism. Not the magnetism of lodestones or compass needles, but something vaster, something planetary. This is the birth of the geodynamo. It begins not with a spark but with a slow turn. The Earth itself rotates, and so too does the outer core, though not uniformly. It sloshes, shifts, and rotates in layers differential motion that wraps iron-rich fluid around itself, forming loops of electric current. And where there is current, there is magnetism. The geodynamo is not a device, but a consequence, an emergent dance of motion and charge governed by the laws of electromagnetism and fluid dynamics. At some point, billions of years ago, this system reaches a threshold. The field strengthens enough to extend beyond the core, beyond the mantle, and into the rocky crust above. Eventually it reaches far into space, forming what we now call the magnetosphere, a cocoon of invisible force lines, stretching thousands of kilometers in all directions, wrapping the Earth in an ever-shifting sheath. But here in these first stirrings it is small and unstable. Its direction may waver, its strength may falter. Perhaps it flickers in and out like the earlier stars in the night sky. But the foundation is laid. It is not known exactly when Earth's magnetic field began. Estimates vary. Some scientists point to magnetic minerals in 3.5 billion-year-old Australian rocks, while others look to ancient zircons that may carry whispers of magnetism as far back as 4.2 billion years. These zircon crystals are tiny, no bigger than a grain of sand, but within them lie clues, paleomagnetic hints of fields that once existed. Their alignment, their trace magnetism, suggests a field strong enough to shield Earth from solar wind even before plate tectonics fully shaped the planet's surface. If this is true, then Earth's magnetic field predates complex life, predates the Great Oxygenation. Event predates even the solidification of the inner core. It may have been among the first planetary systems to stabilize a quiet protector, long before any organism crawled or breathed. Yet even in these early stages, mysteries abound. Why did the field appear when it did? Did the core crystallize from the center outward, slowly forming the solid inner core that now anchors the dynamo? Or did a different mechanism drive those ancient motions, perhaps a chemical gradient or a layered composition in the liquid core? The exact drivers remain unknown. We understand the physics and principle. Moving conductive fluid under rotation produces a magnetic field. But the details how that motion sustained itself over billions of years, how it survived planetary bombardments, how it evolved through deep time remain elusive. The geodynamo is a system too vast to replicate, too slow to observe directly, and too deep to reach. We learn of it only through its surface effects, through the alignment of ancient minerals, and the pull on modern instruments. There is irony here, gentle and cold. That something so fundamental, so planet-defining is invisible to the eye. That it arises not from the sky or the stars, but from the darkest part of the Earth, its molten iron belly. That while mountains rise and fall, while oceans shift and freeze, the magnetic field endures flickering and reforming, yet always returning, and that despite all this, the source of our planetary shield lies in the same chaotic churning that once melted. The surface cracked the crust and forged volcanoes of liquid fire. The magnetic field, born of inner violence, becomes the Earth's first line of defense against external violence. Another irony: magnetism has no scent, no taste, no color, yet it defines the habitability of our world. Without it, solar wind would strip the atmosphere in great gaseous tides as it did on Mars. Cosmic rays would scald the surface unchecked, and fragile molecules like DNA would falter beneath the constant bombardment. Life as we know it would either never arise or would be forced to remain deep below the surface, hidden in oceans or crustal refuges. The quiet emergence of the magnetic field then is not just a geophysical event, it is a precondition for life. And yet life plays no part in its formation. There is no feedback loop, no biological role. The geodynamo hums regardless, and still it hums today. Though changed, though wandering, though at times weak or reversed, the magnetic field continues its subtle labour shaping auroras, guiding migration, shielding satellites, and whispering across compasses the direction of north. But that legacy begins here in this deep ancient movement of iron beneath stone. Not a spark, not a moment, but a beginning made of motion, a field that stirs, that wraps the planet, that begins not with fire or light, but with turning. Quietly, steadily, the Earth begins to shield itself. Within this deep planetary breath, where the outer core turns in vast soundless spirals, the magnetic field finds its rhythm. It is no longer just a flickering pulse or intermittent flare, but a continuous self-sustaining system, an invisible engine locked within the rotation of the Earth. The geodynamo has stabilized. The loops of current, stirred by convection and twisted by the planet's spin, wrap themselves into a coherent structure. Field lines emerge from the poles, arc through the magnetosphere, and dive back down on the other side, encircling Earth like threads of unseen silk. The field has found its pulse a slow, rhythmic pattern, not bound to surface life or seasonal changes, but to the deep, unhurried cycles of molten metal and planetary spin. It breathes in time with the Earth's rotation and cools in step with the planet's gradual loss of internal heat. From this moment forward, Earth carries magnetic shield into every chapter of its history. The field does not remain static. Though it may appear stable across a human lifespan, it is in constant flux. Its poles wander, its strength rises and falls, and its shape warps subtly under the influence of core currents, mantle plumes, and tectonic drift. Even now, the North Magnetic Pole inches steadily toward Siberia, tugged by asymmetries deep below. But this flux is not a flaw. It is the signature of life within the field itself. Like the shifting weather patterns of the atmosphere or the currents in the ocean, magnetic flux reveals a system alive with motion and complexity. It is a pattern not of randomness, but of ceaseless reformation, a field adjusting itself in response to flows no eye can see. At times, the field grows stronger, its grip on the magnetosphere tightening, extending the protective shell that shields Earth from charged solar particles. At other times, it weakens, thins, allowing more radiation to penetrate. These changes are not tied to any external force, they emerge from the interior, from the ever-shifting balance of heat rotation and fluid flow in the outer core. And though we cannot hear it, the field hums, not audibly but electromagnetically, generating low-frequency signals that ripple through the atmosphere, detectable by sensitive instruments as a slow, planetary murmur. It is a sound of sorts, a vibration of the deep Earth, continuous and calm. Magnetic field lines, though invisible, are not abstract. They exert real force on charged particles, guiding them along curved trajectories, deflecting the solar wind in sweeping arcs and channeling energy toward the poles. There where the field dips closer to Earth's surface, streams of electrons enter the upper atmosphere, exciting oxygen and nitrogen molecules. The result is light auroras, not just spectacle but a visible signature of the field's living structure. These luminous curtains, green and red and violet, trace the invisible architecture of magnetism across the sky. They are not static, but shift in real time with fluctuations in the field. To early observers, they must have seemed like divine signals, but their source lies deep within the molten earth, carried upward through layers of rock and air by the motion of iron. And still, despite our growing knowledge, many aspects of the field remain unresolved. Why, for example, does the field sometimes undergo rapid fluctuations over decades or centuries, while at other times it holds steady for millions of years? What triggers these shifts? What internal thresholds must be crossed for the field to change direction or weaken dramatically? Our models suggest possibilities, but no complete answers. We simulate the dynamo in computers, but no laboratory can reproduce its full scale, its pressure or its heat. The outer core at over 4,000 degrees Celsius and under immense pressure is a realm beyond direct access. We observe its effects, infer its structure from seismic waves, and measure the field it produces at the surface, but the true choreography remains hidden. There is a quiet irony here that this most essential planetary system, the one that shields Earth and enables the persistence of atmosphere and life, is also the most inaccessible. Unlike the crust or the oceans, the core cannot be drilled or photographed. Its workings are reconstructed from indirect clues, paleomagnetic signals in ancient rocks, fluctuations recorded in centuries-old navigation charts, and tiny anomalies tracked by orbiting satellites. We know the field is real because of what it does, but its source remains concealed, locked behind layers of stone and heat and time. Another irony, the field's presence is most visible at the margins at the edges of the planet, not its centre. Auroras flare near the poles. Compass needles respond at the surface. Satellites skim its outer boundaries. But the origin of all this lies deep inside, far from any light in a place older than continents. The geodynamo works without light, without sound, and without pause. It has no seasons. It marks no days, and yet it pulses without fail, reconfiguring itself as needed, maintaining a form of planetary continuity that outlasts even the longest geological processes. To compare it to anything human is to shrink it. Yet a gentle analogy lingers. It is like a planetary heartbeat, slow, invisible, vital. But unlike the hearts of living beings, this one is made not of tissue, but of metal, not of cells, but of convecting plasma. Its rhythm is measured in millennia, its silence vast, its power absolute. It shields us not because we are here, but simply because the core turns. Whether life had emerged or not, the field would still form, still rise into the sky, still shape the interaction between planet and star. For now, the field holds. We live in an age where the geodynamo continues to function, where compasses still point north, and where satellites and auroras trace the contours of this ancient force. But all of this, every needle swing, every shimmer of light, every pulse of protection, originates in a place we cannot see, in motions we cannot stop, in a process older than oxygen, older than oceans. Earth turns, and the iron turns within it. From that motion, the field emerges, and in that field our planet remains encased in a veil of quiet force. Locked within the oldest minerals on Earth, there are remnants of something silent yet persistent, traces of magnetism imprinted in stone like breath caught in glass. These are the paleomagnetic signals preserved in zircon crystals some over 4 billion years old found in the ancient terrains of Western Australia. Zircons are tiny, no wider than a human hair, but they are geological archivists recording conditions from a time when Earth was still cooling from its formation. Within their crystal lattice iron-bearing inclusions can trap the orientation of magnetic fields present when the zircon formed. These orientations, fixed for billions of years, are now being decoded to reconstruct the infancy of Earth's magnetic life. In these shards of deep time, scientists have found evidence that a magnetic field may have existed long before the solidification of the inner core, perhaps even as early as 4.2 billion years ago. If true, it suggests the geodynamo was active not just early but staggeringly early, offering protection long before the surface became stable or life took hold. It reshapes our sense of planetary history, hinting that the shield preceded the organisms it would one day protect. Zircons are not the only witnesses. Later in Earth's history, as continents formed and drifted, as oceans opened and closed, basaltic lava flows cooled and hardened, capturing the direction and strength of the prevailing magnetic field. These ancient volcanic rocks spread across the globe form a layered archive of geomagnetic history. As each flow solidified the iron minerals within, aligned with the ambient field, recording not only its polarity, but its intensity and orientation. From these records, scientists have reconstructed hundreds of millions of years of magnetic reversals, anomalies, and quiet periods. They are like pages in a planetary journal, each etched with the invisible handwriting of magnetism. Still, the zircon record remains elusive and difficult to interpret. The signals are faint, often at the edge of detectability and subject to alteration by heat pressure and time. Some scientists debate whether the oldest magnetic signatures are genuine or artifacts of later thermal events. Others argue over the field's strength and stability in these early epochs. Did Earth's field flicker weakly for eons before stabilizing? Was it intermittent waxing and waning like a distant beacon? Or did it arise swiftly, a fully formed shield conjured by internal motion? These questions remain unresolved, and each newly analyzed crystal invites more uncertainty, not less. It is a paradox of deep time. The closer we look, the more the past dissolves into ambiguity, and yet the field persists in memory, if not always in clarity. There is something quietly poetic in the idea that the history of Earth's magnetic field is not written in sweeping landscapes or catastrophic events, but in microscopic grains and the orientation of atoms. That this global planet-wide system leaves its signature not in loud evidence, but in delicate alignments preserved within individual mineral structures. Iron atoms spinning, charged, aligned, become archivists of planetary magnetism. One by one they fix themselves in place as molten rock cools their direction, silently echoing the unseen field. No thunder, no flash, just orientation preserved. It is the geology of restraint. There is also irony here. These ancient clues are durable enough to survive eons, but fragile in interpretation. We build elaborate theories upon the orientation of magnetic domains barely microns across. In these interpretations we find stories of Earth's first breaths of the moment when internal motion crossed some invisible threshold and began to generate a coherent magnetic field. But the zircons do not speak. The rocks do not testify. They only hold position, offer resistance to heat, and whisper faintly of fields long collapsed. Yet within this silence lies a profound mystery. If Earth's field existed 4 billion years ago, what powered it? The standard model of today's dynamo includes the crystallization of the solid inner core, which releases latent heat and drives convection in the surrounding liquid iron. But this process likely began only around 1:1. 5 billion years ago, far later than the magnetic evidence in zircon suggests. So what mechanisms sustained the field before the inner core existed? One possibility is compositional convection. As lighter elements separated from the denser molten iron, they may have risen through the core, generating currents independent of crystallization. Another is that the young core cooled rapidly enough to drive sufficient convective force on its own. Neither explanation is fully satisfactory. The early Earth remains a world of partial answers, its history written in half-light, its processes inferred from the tilt of minerals and the direction of ancient fields. These uncertainties do not lessen the field's importance, they magnify it. The fact that the magnetic field might have formed so early means it was present during the most vulnerable period of planetary evolution, when the solar wind was stronger, the atmosphere still thin, and the surface prone to sterilizing radiation. A magnetic shield in those conditions would not only deflect harmful particles, but might also slow atmospheric loss, preserving volatile compounds critical for the emergence of water and eventually life. It may have protected the ingredients of habitability long before life itself arose. And in this, the magnetic field becomes not just a product of geology, but a quiet precondition for biology. We often think of evolution as a surface story of continents shifting, of oceans forming, of cells dividing. But beneath all of this, unseen and uninterrupted, the field continues. It requires no witness, no living thing to justify its presence. It emerged before life, and it may outlast it. In the zircon record in ancient lava, in the slow drift of poles across paleomagnetic maps, we trace a narrative not of organisms, but of alignment, of orientation, in a world without direction. The Earth spins, iron moves, and the field forms. It forms again and again across eras, through reversals, through lulls, through epochs when no eye observed, and no being knew what protection meant. The story of magnetism is a story of resilience, without drama, of presence without display. It is a quiet force etched into the smallest structures, a veil formed by the invisible hand of planetary motion. And though it flickers in and out of certainty, the message it carries is unwavering. The Earth has always turned, and in that turning the field has always tried to hold. Beneath the oceans where continents do not tread, Earth's magnetic history is carved in long, silent bands of volcanic rock. Along the mid-ocean ridges where tectonic plates drift apart, magma rises from the mantle and cools rapidly as it contacts seawater, forming fresh basaltic crust. This new crust, rich in iron-bearing minerals, captures the direction and polarity of the planet's magnetic field at the moment of its formation. Layer by layer, as the seafloor spreads outward over millions of years, it creates a magnetic pattern striped like tree rings, but far more ancient. These symmetrical magnetic anomalies flanking either side of oceanic ridges record a story not of life or surface weather, but of magnetism itself, its reversals, its wanderings, its hesitations. The ocean floor becomes a vast geological tape recorder, preserving the slow oscillations of Earth's invisible field across hundreds of millions of years. This pattern was first recognized in the 1960s during the birth of plate tectonic theory. Marine surveys revealed stripes of alternating magnetic polarity, normal and reversed, spaced evenly across the Atlantic seafloor. At first, the regularity of the pattern seemed improbable, almost artificial, as if the planet were quietly switching its internal compass on some hidden metronome. But further studies confirmed the global nature of the phenomenon. The same magnetic striping appeared in every ocean basin, synchronized with known periods of geomagnetic reversal. These bands did not align with continental events or surface catastrophes. They obeyed only the deep logic of the core. In them we see a quiet signature of the geodynamo's restless nature. Magnetic reversals do not occur at regular intervals. The times between them, known as crons, can stretch from less than 100,000 years to over 30 million. Some periods, such as the Cretaceous normal superchron, lasted nearly 40 million years without a reversal, while others, like the late Jurassic, saw reversals occur in rapid succession. No clear pattern governs this behavior. The geodynamo appears to drift through stable and unstable regimes like a river that sometimes meanders and sometimes floods. This lack of predictability is a mystery. The underlying physics is deterministic, but the system itself is chaotic, sensitive to minute changes in fluid flow heat distribution and rotational forces deep within the core. These magnetic reversals are not merely curiosities, they're global events detectable across all continents and seas, in igneous rocks, sedimentary basins, and deep-sea cores. During a reversal, the field weakens, becomes multipolar, and may all but vanish for a time. The transition, though slow by human standards, is rapid on geological timescales, often unfolding in less than 10,000 years. In some cases, evidence suggests reversals may have occurred in as little as a few centuries. This raises questions about the stability of Earth's magnetic shield during these periods. Would solar wind and cosmic radiation have penetrated more deeply? Would the increased exposure have affected surface life or atmospheric chemistry? The geological record offers few direct answers. No mass extinctions clearly coincide with reversals. Life, it seems, has persisted through them all, quietly adapting beneath a weakening sky. There is an understated irony in this resilience. We think of the magnetic field as a protective barrier essential for shielding DNA from mutation, for preserving the atmosphere, for guiding migratory species. And yet it has failed and reformed countless times without triggering planetary catastrophe. Either the field's shielding effect is less critical than assumed, or Earth's biosphere is far more adaptable than we understand. Perhaps both are true. The field reverses, poles wander, shielding weakens, but life continues adjusting beneath the slow pulses of magnetism, indifferent to the direction of north. At the same time, the reversals themselves become markers, global timestamps used to synchronize the geologic record. In stratigraphy, they serve as guideposts. The Brunhes-Matuyama reversal at 780,000 years ago, the Gauss-Gilbert reversal at 2.6 million, the Jaramillo subchron, the Olduvai chron. These names echo like constellations through paleomagnetic literature. Each reversal marks not only a change in the field, but a moment of global synchrony, a pause in the drifting uncertainty of deep time where scattered rocks align under a single magnetic truth. They offer rare moments of clarity in a record otherwise composed of erosion, metamorphism, and incompleteness. There is also a poetic asymmetry in the field's reversals. While we know they occur, we do not know when the next one will come. The field does not weaken in a regular, predictable way. Its strength fluctuates but does not follow a linear trend. Today the field is approximately 10% weaker than it was a century ago, and a notable low-intensity region, the South Atlantic anomaly, has expanded across parts of South America and the Southern Atlantic Ocean. This has led some to speculate that we are entering the early stages of a reversal. But the geodynamo does not reveal its plans. It may reverse in 1,000 years or hold steady for another 10 million. There is no countdown, no warning, only motion, only flux. Still, the record on the ocean floor remains quietly spreading outward as plates drift. It is not dramatic. There are no fanfares in basalt, no proclamations in pillow lava, just alignment frozen at the moment of cooling, locked in the crystalline structure of minerals like magnetite and hematite. And with each new eruption at the ridge, the tape extends, carrying the planet's magnetic heartbeat forward by another breath. The ocean floor becomes a scroll endlessly written, seldom read. This quiet archive tells us something unexpected, that Earth's field is not merely a stable shield, but a dynamic presence fluctuating in strength and form, reversing when the system requires it, reforming when conditions allow. It has no allegiance to constancy, no need for symmetry. It exists as an emergent property of the core's motion, a consequence, not a goal. And in that it mirrors much of the planet's behaviour, unplanned, unequally paced, and deeply indifferent to surface rhythms. So the ocean spreads, the basalt cools, and the field continues its quiet reversals. No signal sounds when north becomes south. No light shifts when lines of force dissolve and reconfigure. But somewhere in the molten layers of the core a pattern has changed. The loops of current have twisted, the flows have reorganized, and the planet's veil of magnetism has flipped. To us these are abstractions. To the Earth they are simply motion. The rhythm of Earth's magnetic field is not always one of reversal and renewal. There are also intervals of uncanny stillness, long epochs during which the field does not reverse, does not falter, but holds its polarity with a steadiness that defies expectation. These supercrons, as they're called, stretch like magnetic deserts through geologic time. The Cretaceous normal. Supercron, for instance, endured for nearly 40 million years without a single reversal, spanning a time when dinosaurs flourished, oceans rose, and the continents drifted toward their modern arrangement. Beneath all of this surface drama, the magnetic field remained unchanging, resolute in its orientation, a constant presence in a world of flux. Then without warning it reversed as though emerging from a dream. The question remains why. Why does the geodynamo sometimes fall into prolonged stability, only to awaken again into a pattern of reversals and excursions? No single theory has resolved this. Some researchers suggest that subtle changes in the pattern of convection within the outer core, perhaps driven by mantle plumes or by the cooling rate of the planet, could influence the stability of the dynamo. Others propose that fluctuations in the amount or distribution of light elements such as sulfur or oxygen in the outer core may alter its flow characteristics. Still others point to the role of the inner core itself, whose growth and asymmetry may exert a stabilizing or destabilizing effect depending on its geometry. But all of these explanations remain speculative. We're trying to model a system that has no precedent, no laboratory analogue, and no direct observation. It is a problem of scale and inaccessibility, of trying to deduce the deep heart of the planet from the surface signatures of long cooled rocks and the whispering tilt of compass needles. In this, the field again reveals its deep indifference to human understanding. Its behaviours do not conform to patterns we find satisfying. They do not follow simple periodicity, nor do they align with external events. There is no link between reversals and asteroid impacts, no clear correlation with extinction events, no comforting symmetry. The field, like the planet itself, moves according to principles that are governed not by narrative, but by physics, by temperature gradients, Coriolis forces, density differentials, and the complex equations of magnetohydrodynamics. Yet from these mute interactions, a vast and enduring structure emerges, one that not only persists through eons, but changes its form in ways both unpredictable and strangely serene. Occasionally, however, the field behaves even more erratically. Instead of fully reversing, it may weaken and drift into a temporary partial state, a magnetic excursion. These excursions differ from full reversals in that the field's polarity does not complete a full flip. Instead, the magnetic poles may wander far from the geographic poles, weakening to a fraction of their usual strength, only to return to their original configuration. One of the most studied of these events is the Lachance excursion, which occurred around 41,000 years ago. During this brief interval, the magnetic field nearly collapsed, weakening to less than 10% of its normal strength. The poles moved rapidly across the globe, and for a few centuries the field resembled that of a bar magnet tossed into chaos. Then slowly it returned. The entire episode lasted perhaps 1,000 years, barely a blink in geological time, yet potentially significant for the surface conditions of Earth. What effect did such an excursion have? Some studies suggest that increased radiation during the Lachance event may have altered atmospheric chemistry, leading to a spike in the production of cosmogenic isotopes like beryllium-10 and carbon-14. There are even tentative correlations proposed between this period and minor disruptions in climate patterns or human migrations, though the evidence remains inconclusive. What is clear is that the magnetic field is not a static presence, but one capable of sudden lapses, moments when the shield thins, the poles wander, and the deep processes of the core become visible not through direct observation, but through their absence. The irony is soft but profound. The field which exists only through motion can sometimes fall into stasis. The system designed by nature to be dynamic, to churn to reverse, can settle into a kind of dormancy for millions of years. And the same system built to be robust and self-correcting can also collapse briefly into weakness and uncertainty. In both cases, the result is the same: a planet enveloped in a field that is neither predictable nor entirely reliable, yet remains over the longest timescales remarkably resilient. What does this teach us? Perhaps only that constancy and instability are not opposites but partners. The magnetic field endures not in spite of its reversals but because of them. Its ability to reconfigure to fall into stillness or stutter into excursions is not evidence of failure, but of life of motion within a liquid heart that responds to forces far deeper than we can touch. It is not a machine with a schedule, but a system balanced on fluid thresholds, governed by processes measured in kilometers of pressure and millions of degrees of heat. And still it continues. Whether holding firm for 40 million years or shifting within centuries, the field does not ask permission, does not announce its changes. It simply flows, expands, collapses, and reforms in a pattern as old as the planet. Each reversal or excursion leaves a subtle trace in stone, a band on the ocean floor, a shift in remanent magnetization, a curve in the record of polar wander. These are not the marks of catastrophe, but of continuity, etched not in disaster, but in drift. So we look to the rocks, we core the seabeds, we drill the basalts, we analyze the zircons and trace the field's history, not through stories, but through alignment. It is a history, without voices, without witnesses, without drama, only quiet turns and long silences, only the molten memory of iron and the stillness of hardened stone. The field may reverse again, or fall into another long stillness, or wander in ways we cannot yet foresee. It will not explain itself, it will only turn. On the surface of the planet we navigate by a compass that points north, a simple gesture grounded in something vast and invisible, the slow, meandering dance of Earth's magnetic poles. These poles are not fixed, they drift. Each year the North Magnetic Pole migrates sometimes by 10 kilometers, sometimes by 50, pulled by asymmetries in the magnetic field generated deep below. In recent decades the movement has accelerated, shifting the pole away from the Canadian Arctic toward Siberia at an unusually fast rate. It is not a straight path, but a curve shaped by the complexity of the geodynamo, an interplay of molten iron currents in the outer core that reshape the magnetic topology without ever revealing their origin. The field is in motion, and so too is our concept of direction. North is not where it used to be, and it may not stay where it is. This pole drift is not a new phenomenon. Historical navigation charts some centuries old already record subtle shifts in magnetic orientation. Explorers in the age of sail noticed deviations between true north and magnetic north variations they could not explain but were forced to adjust for. Today, satellite measurements have made these variations more precise, mapping the wandering poles with remarkable accuracy. We can see the poles leave trails across the polar region's slow arcs that remind us that what seems stable is in fact perpetually in flux. The planet's field is not a rigid structure but a flowing one, as responsive to internal turbulence as a plume of smoke is to wind. And in this movement lies both continuity and uncertainty. The field remains, but its form is always shifting. The cause of this drift lies in the subtle imbalance of the field's two hemispheres. Unlike a perfect bar magnet, Earth's magnetic field is not symmetrical. Its strength, direction, and multipolar distortions vary across the globe, influenced by irregularities in the flow of molten metal, by topographic features at the core mantle boundary, and perhaps by complex feedbacks between thermal and compositional convection. These forces combine to push the magnetic poles along paths that defy simple prediction. Sometimes they pause, sometimes they lurch forward, sometimes they reverse their trajectory entirely. What we observe is not a deterministic migration, but a magnetic walk across the surface of a restless world. This wandering has real effects. Navigation systems, both analog and digital, rely on accurate magnetic models, and as the poles shift, those models must be recalibrated. The World Magnetic Model used by NATO and civilian systems alike is updated regularly to reflect changes in the field. Yet the speed of recent drift has sometimes outpaced the update cycle, prompting emergency revisions. Pilot surveyors and autonomous vehicles all must account for a planet whose invisible framework of orientation is slipping beneath their feet. There is no crisis here, only adjustment. But the lesson remains: the world beneath our instruments is not fixed. There is irony in how we treat the magnetic field as a stable reference, how we build our systems around the idea of magnetic north, only to find that the field itself refuses to hold still. It is like using the surface of a river as a ruler. The field is a guide, yes, but it is also a current, its lines of force constantly redrawing themselves in response to deep movements we cannot see. And yet, for all its fluidity, it remains one of the most reliable planetary features. Even as it drifts and distorts, the field continues to exist, continues to shield and structure the space around Earth. It is dependable not because it is still, but because it is enduring. There are quiet mysteries here. Why does the South Magnetic Pole move so differently from the North? Why do certain regions of the field, like the South Atlantic anomaly, behave in ways that defy global trends? What causes the hemispheric imbalance in magnetic strength, with the southern field often more diffuse and variable than the northern? These questions remain open. We have simulations models that suggest plausible explanations, but the true answers are locked beneath thousands of kilometers of rock and molten iron, in a realm where no probe can reach. The outer core is a place of turbulent flow of chaotic convection, shaped by conditions we can only approximate. From its shifting currents emerge the global field, and from that field emerge the poles we follow. Even the notion of pole is a simplification. The magnetic poles are not singular points, but diffuse region zones where the field lines converge or emerge depending on direction. As the field becomes more multipolar during reversals or excursions, these regions can fragment, multiply, or vanish entirely. There may be times when the planet has more than two magnetic poles or none at all in the traditional sense. During such periods, the field weakens and the lines of force become tangled and complex. Still, the Earth turns the core churns and the field persists sometimes as a coherent dipole, sometimes as a fluctuating pattern of partial alignments. From a broader perspective, the wandering of the poles is just one expression of the field's deeper truth that it is an emergent property of motion. Nothing about the magnetic field is static. Its origin lies in the turning of the Earth, the flow of molten iron, the asymmetric currents shaped by rotation and heat. Its existence is a process, not a structure, a phenomenon defined not by what it is but by what it does, and what it does is move, through time, through stone, through sky. Still, the movement of the poles offers something poignant. It is a reminder that direction itself is a kind of illusion, a temporary agreement between us and the planet we inhabit. What we call north is not a fixed star, but a compromise between geography and magnetism. What we navigate is not a stable world, but a shifting one guided by a field that even in its flux remains more faithful than any landmark we can build. The compass needle wavers, but it always points somewhere, and that perhaps is enough. So the poles continue their silent march, tracing slow paths across ice and sea, leaving no trace but the recalibration of instruments and the quiet footnotes of scientific models. Beneath them the core flows, around them the field drapes the planet in an ever-shifting veil. Above them the auroras flicker and curl, and through it all the earth spins steady, unhurried, magnetic. Far below the surface, where no light penetrates and no living organism has ever tread the outer core, continues its endless rotation. Within this metallic sea, something remarkable happens as volcanic rock cools at the surface, as tectonic plates grind and shift as seasons pass unnoticed. Tiny grains of iron-bearing minerals in the upper world quietly align themselves with the magnetic field generated in this subterranean furnace. When lava cools and solidifies, when sediments settle and compact over millennia, these grains preserve the orientation of the field at that precise moment. Each is like a microscopic compass, frozen in time, a fragment of direction captured in stone. This is remanent magnetization, a natural recording of the field's orientation and strength, made without instruments, without intention, and yet invaluable to science. It allows paleomagnetists to reconstruct the history of Earth's magnetism, from rocks pulled from cliffs, cores, ocean basins, and ancient lake beds. These mineral memories form a scattered but growing archive, silently preserving the choreography of the invisible. The process is elegant in its simplicity. When certain iron-rich minerals like magnetite or hematite cool below their Curie temperature, their magnetic domains lock in the ambient field direction. The orientation persists even if the field changes later, making each rock a snapshot of geomagnetic conditions at the time of its formation. Over geological timescales, these records become layers forming patterns that mirror the larger fluctuations of the geodynamo. By sampling sequences of volcanic flows, sedimentary strata, or even baked archaeological materials, researchers can read the field's history backwards, when it reversed, when it weakened, when it surged. The timeline extends not just to the deep past, but into human history. Magnetization, preserved in fired bricks, kilns, and hearths, offers clues to magnetic conditions during the earliest civilizations. And yet, despite the precision of these natural recordings, uncertainty lingers. Magnetic minerals can be remagnetized by later heating or deformation. Chemical changes can obscure the original signal. Rocks are not perfect archives, they can be disturbed, altered, or eroded. The task of the paleomagnetist is to discern the true signal from the noise, to read the record not as a literal text but as a palimpsest, where older inscriptions mingle with newer traces. This uncertainty, rather than weakening the field, adds to its quiet mystique. We do not possess a flawless history of the magnetic field, only scattered memories overlapping and incomplete, but they are enough to tell us that the field has never stood still. Among the more poetic aspects of this mineral archive is its ability to record pole wander. Over long time scales, the continents themselves drift across the surface of the Earth, carried by the movement of tectonic plates. This drift means that rocks fixed in place today were once located in entirely different latitudes. By comparing the magnetization of rocks of different ages and positions, scientists can reconstruct the apparent path of the poles relative to each continent, a path that, when corrected for plate motion, reveals the true motion of the field itself. These polar wander paths trace great arcs across the globe, revealing how the field has shifted, rotated, and reoriented through deep time. They are not just geological data, they are tracings of an unseen hand moving across the planet's surface over hundreds of millions of years. A gentle irony rests in how this invisible field, this force we cannot see or touch, leaves its most enduring signature in the hardest of substances. The dance of electrons in molten iron, the flowing turbulence of the outer core, the vast geometry of magnetism, all of it captured in the crystallization of stone. The minerals do not understand what they record. They respond only to physics, to alignment, to temperature, and yet their obedience becomes revelation. From their silent alignment we deduce the nature of the geodynamo, the timing of reversals, the movement of continents, even the behavior of the solar wind across epochs. One of the more curious applications of this paleomagnetic record is in the study of magnetic inclination, the angle at which magnetic field lines intersect the Earth's surface. Near the poles, the inclination is steep. Near the equator, it is shallow. By measuring the inclination preserved in rocks, scientists can estimate their paleolatitude at the time of formation. This technique has been used not only to track tectonic motion, but to infer past climate zones to model the configuration of supercontinents like Pangaea and Rodinia, and to study the evolution of ocean circulation patterns. A frozen magnetic grain can in this way become a proxy for where a continent once stood, and by extension what climate it may have experienced. The magnetic field becomes a lens through which the ancient world can be reconstructed. Still, the questions persist. How stable are these mineral records over the deepest time? Can magnetization survive multiple metamorphic episodes? What signals have we yet to interpret correctly? The deeper into the past we reach, the fainter the signals become, and yet even the most ancient rocks, the 3.5 billion-year-old formations of the Barberton Greenstone Belt or the Acasta gneiss of Canada, sometimes yield faint traces of alignment, magnetic whispers that suggest a field existed when life was just beginning. Whether these are reliable signatures or thermal illusions remains debated, but the mere possibility that such ancient stones carry within them the direction of a magnetic field formed in Earth's infancy is enough to deepen the mystery. There is a certain beauty in this layered archive, in the idea that every continent carries within its crust a partial memory of the planet's invisible shield. These are not human histories. They do not record kings or wars or seasons. They are deeper, slower, more patient. They are the record of a field that shifts in cycles longer than civilizations, in patterns broader than oceans. The magnetic field in its ceaseless motion leaves behind these still monuments, igneous flows, sediment layers, iron grains in mud, and in them we find direction not just for our compasses but for our understanding of planetary time. So the earth turns and the iron flows and the rocks cool. In this dance between fire and stone motion and stillness, the field is both actor and archivist. It moves above us unseen, even as it inscribes itself beneath us, mineral by mineral, crystal by crystal, without haste and without end. Far above the rocks that hold ancient magnetic memory, beyond the clouds and the shifting atmosphere, Earth's magnetic field unfurls into space, forming an enormous and dynamic structure known as the magnetosphere. Unlike the calm, symmetrical diagrams that depict it in textbooks, the real magnetosphere is distorted fluid and in constant motion. On the day side of the planet, it is compressed by the relentless pressure of the solar wind, a stream of charged particles ejected from the sun at hundreds of kilometers per second. On the night side, it stretches outward in a vast tail that extends millions of kilometers into space, shaped like a windsock flaring behind a moving ship. This magnetotail is not empty. It is filled with plasma-energized particles trapped by the field, and occasionally flares with bursts of energy as magnetic reconnection events snap and reform field lines in distant regions of space. These sudden rearrangements can hurl particles toward Earth's upper atmosphere, triggering luminous auroras and subtle ripples in our electrical systems. All of this occurs invisibly silently beyond human senses, but it defines the boundary between Earth and the cosmos. The magnetosphere is not merely a structure, it is a shield. Without it, the solar wind would directly strike the atmosphere, gradually stripping away lighter molecules into space. This is likely what happened to Mars, a planet similar in size but now magnetically inert. The absence of a global magnetic field left its once thicker atmosphere vulnerable, and over time the charged particles from the sun wore it down. The evidence lies in the traces of atmospheric escape still observed today in the signatures of lost gases detected by orbiting probes. Venus too, with its dense atmosphere, lacks a strong intrinsic magnetic field, and instead possesses an induced magnetosphere, one generated by the interaction between its upper atmosphere and the solar wind. But this induced shield is far weaker and more variable, unable to prevent erosion on longer timescales. Earth alone among these terrestrial neighbours maintains a robust internally driven magnetosphere, a consequence of its churning metallic core and the dynamo within. Within this shield, life has evolved, persisted and flourished. The magnetic field deflects most of the solar and cosmic radiation that would otherwise reach the surface, allowing complex organic molecules to form and remain stable. It protects not just organisms, but the very conditions that allow organisms to exist in an atmosphere rich in nitrogen and oxygen, a climate stable enough for liquid water, and a surface that is not constantly bombarded by high-energy particles. And yet, for all its significance, the field acts in silence. Plants do not respond to it. Most animals cannot sense it. Humans lived millennia before realizing it existed at all. Only certain migratory species, birds, turtles, whales, have evolved biological mechanisms to detect and utilize the field, navigating across oceans and continents by an unseen compass buried somewhere in their cells. For them, the field is not abstract. It is directional, present, real. And still the magnetosphere is not impermeable. During periods of heightened solar activity, solar flares, coronal mass ejections, the volume of solar particles increases dramatically, compressing the field and injecting bursts of energy into its outer layers. Some of this energy reaches Earth, inducing geomagnetic storms that can disrupt satellites, damage power grids, and alter radio communications. These events, though infrequent, are reminders that the field is not a wall but a dynamic buffer, a membrane that bends, flexes, and occasionally lets the sky burn. The auroras, beautiful as they are symptoms of this stress. They occur when charged particles spiral down field lines and collide with atoms in the upper atmosphere, causing them to emit light. The result is a luminous veil rippling with colour, silently tracing the architecture of the magnetic field above our heads. One of the quiet ironies of the magnetosphere is that while it protects life, it also hides the processes that sustain it. The outer core where the field originates is inaccessible. The field lines themselves, though they define the shape of the magnetosphere, are intangible, and the effects of the field, while dramatic in space, remain mostly imperceptible on Earth's surface. We live inside a shield we cannot touch, cannot see, and only recently came to understand. Our satellites map it. Our instruments measure its fluctuations, but its true nature eludes visualization. It is not a thing, but a relation between motion and charge, between interior and exterior, between planet and star. There is also mystery. Why does the shape of the magnetosphere vary so much between geomagnetic storms? Why do reconnection events occur where and when they do? What governs the structure of the magnetotail, and how does it store and release energy? These are questions of space weather, studied by fleets of satellites, by magnetometers, anchored in polar regions, by simulations running across supercomputers. We seek to understand how the shield flexes and how it fails, not because we doubt its importance, but because our dependence on technology has made us newly vulnerable to its disruptions. Yet even in our most sophisticated models, the core of the field remains distant, its origins unreachable, its patterns only partially revealed. The further we extend our reach into space, the more essential the field becomes, and the more invisible its foundation feels. A final irony lies in the fact that the magnetosphere, while protective, also traps harmful particles. The Van Allen radiation belt's donut-shaped zones of high-energy particles encircling the planet are held in place by the magnetic field itself. These belts are dangerous to satellites and to astronauts beyond low Earth orbit. They are a byproduct of the field's structure, not a failure but a consequence. The field does not filter selectively. It traps what it can, protects what it may, and defines a space both shielded and hazardous. In this it resembles the field's nature more broadly, not good or bad, not consistent or chaotic, simply present. It does not serve us, and yet we depend on it. It does not know us, and yet we cannot live without it. The magnetosphere, then, is a reminder that the planet is not an isolated sphere, but a participant in a larger exchange, a dance with the sun modulated by radiation particle streams and invisible force lines. It is not a barrier, but a mediator, a translator between solar violence and terrestrial calm. In its vast, silent arcs, the field enfolds the Earth like a slow breath, expanding and contracting with cycles we barely perceive. It is not stable, it is not permanent, but it endures in motion, in silence, in space. Deep within the Earth, where pressure exceeds 3 million atmospheres and temperatures rival the surface of the Sun, the molten iron of the outer core encircles a solid inner sphere. The inner core, a dense ball of crystallized iron and nickel roughly the size of the Moon. This inner core does not sit still, it rotates possibly at a slightly different speed than the mantle and crust, above a phenomenon known as superrotation. Though separated from the surface by over 5,000 kilometers of rock and liquid metal, this silent glowing heart plays a critical role in sustaining the geodynamo. As it slowly grows over geological time, crystallizing from the outer core's fluid, it releases both heat and lighter elements into the surrounding liquid iron. These processes in turn drive buoyant convection currents, spiraling flows that feed the dynamo's motion. The inner core is not simply a passenger in the story of magnetism, it is a generator, a stabilizer, and perhaps even a source of the field's longevity. Its formation marks a transition in Earth's magnetic history. Before the inner core existed, the geodynamo may have been powered solely by thermal convection, the gradual cooling of the planet and the movement of hotter, less dense iron toward the surface of the core. But thermal convection alone, without the aid of compositional convection or latent heat release, would not sustain the field indefinitely. At some point, perhaps around 1 to 1.5 billion years ago, the inner core began to crystallize. This process released not only heat, but also light elements like silicon sulfur or oxygen into the outer core, enhancing the density contrasts that drive fluid motion. The result was a reinvigorated dynamo, one that has remained surprisingly stable ever since. The presence of the inner core therefore may explain the increased regularity and strength of the magnetic field over the latter half of Earth's history. But mysteries remain. We do not know the exact age of the inner core. Estimates vary widely, with some suggesting it began forming as early as 2 billion years ago, others as late as 500 million. The uncertainty lies not in theory but in evidence. The core is beyond our reach, no instrument can measure it directly, and no borehole will ever reach its boundary. We infer its properties from seismic waves, which slow down or speed up depending on the materials they pass through. These measurements reveal that the inner core's anisotropic waves travel faster along certain directions, suggesting a crystal structure with preferred orientations. What causes this alignment? Is it the slow rotation of the core itself, stretching the iron crystals into columns? Is it the uneven growth of the core with more crystallization occurring in some regions than others? No answer is certain, and yet the pattern is clear. Something within the inner core is shaping the very symmetry of the planet's deepest region. There is a quiet irony in the fact that this most central part of the Earth, this seed of solidity within the molten depths, is the least accessible. It is closer to us than the Moon, yet more alien in composition and more unreachable by far. Our only tools are echoes, seismic reverberations from earthquakes and nuclear tests, ripples that pass through the Earth's interior and return distorted. From these distortions we build models. We draw cross-sections, simulate flows, chart growth rates. But the core remains an abstraction. We have never seen it, never touched it, never sent a probe or received a sample. It exists entirely in inference, a structure whose presence is certain, but whose details are perpetually shifting under layers of data and theory. Still, from this deep, unknowable heart comes something profoundly consistent: the magnetic field. It is a surface phenomenon, yet it originates in motion far below. Every reversal, every wandering pole, every fluctuation in field strength begins with the patterns of movement in the outer core, and these in turn are influenced by the properties of the inner core, its growth, its heat, its rotation. In this sense, the inner core is not only central in position but in causality. It modulates the behavior of a field that shapes not only Earth's magnetic environment, but also its geological and biological evolution. Without the inner core, the field might have decayed long ago. Without the field, the surface might have remained barren, exposed to solar radiation, and stripped of atmosphere. And yet the inner core asks for no recognition. It offers no signal of its presence, no observable light, no seismic roar. It grows in silence, grain by grain, in the deepest darkness. Some scientists speculate that the inner core is not uniform, that it contains layers of its own, possibly with a different crystalline phase at its very center. This innermost inner core, perhaps just a few hundred kilometers across, might have distinct properties, including a different orientation or composition. If true, it suggests a deeper level of structure, a core within the core, an even more ancient crystallization event recorded in atomic alignment. Whether such a region exists is still debated. The signals are faint, the models complex, and the implications uncertain. But the possibility deepens the mystery. If confirmed, it would mean that the Earth has nested hearts, each one marking a stage in its cooling, each contributing to the invisible engine that drives the field. And so the inner core continues to grow. Each year a fraction of a millimeter of molten iron solidifies at its surface, joining the lattice of atoms already locked in place. This process is so slow as to seem motionless, and yet over hundreds of millions of years it accumulates. The core expands. The outer core loses heat. The convection changes. The field responds. There is no boundary where one process ends and the other begins, only a continuum of motion and transformation, of cooling and crystallizing, of flow and alignment. The Earth breathes through its iron heart, and the magnetic field is the breath we cannot see. There is no drama here, no eruption or collapse, only an enduring presence. At the very centre of the world lies a seed of stillness, and around it the liquid metal turns. From that motion comes the field, and from that field the world is shaped. The magnetic field, though generated deep within the Earth's core, leaves its subtle fingerprints across the surface and even beyond, manifesting in anomalies regions where the strength or direction of the field deviates unexpectedly from the global average. These magnetic anomalies, often spanning hundreds of kilometers, are not caused by changes in the core itself, but by variations in the composition thickness and magnetization of rocks in the crust and upper mantle. They form a patchwork of magnetic textures, quiet distortions in the field shaped by long-cooled lava flows, buried mineral belts or tectonic structures. Aircraft and satellites equipped with magnetometers glide over these patterns, mapping invisible contours across deserts, oceans, and frozen tundras. Each anomaly is a silent witness to ancient geological processes, collisions of continents, eruptions of basaltic flood plains, the upwelling of mantle plumes. They do not move with the daily shift of the poles, but remain fixed geological scars wrapped in magnetism. One of the most enigmatic of these is the South Atlantic anomaly, a vast region stretching from South America to southern Africa, where the magnetic field is markedly weaker than elsewhere at similar latitudes. Here the shielding effect of the magnetosphere is thinned, allowing a greater flux of solar and cosmic radiation to penetrate toward the Earth. For satellites in low Earth orbit, especially those passing over this zone, the anomaly poses a quiet hazard. Electronic systems experience more frequent glitches, radiation doses increase, and instruments must be shielded or temporarily powered down. Despite extensive study, the origin of the anomaly remains unclear. Some suggest it may be linked to an irregular patch of reversed flux in the outer core, a zone where the field points downward instead of upward, locally cancelling out the surrounding field lines. Others connect it to the tilt of the dipole itself, or to deeper heterogeneities at the core mantle boundary. But no consensus exists, only a growing sense that the field, though global, is textured with complexity. These magnetic anomalies, though subtle, have become essential tools in understanding Earth's past. In marine geology, they are used to chart the age of the seafloor. Each pair of magnetic stripes on either side of a mid-ocean ridge corresponds to a reversal in the geomagnetic field. By measuring their spacing and orientation, scientists can reconstruct the rate of plate spreading the shape of ancient oceans and the history of tectonic movement. In mineral exploration, anomalies hint at the presence of iron-rich ore bodies buried beneath soil or forest. In archaeology, they reveal the outlines of lost cities and ancient hearths, where human fires altered the magnetic properties of the soil. Even in planetary science, anomalies extend their reach on the Moon, and Mars' crustal magnetism has been mapped in detail, revealing remnant fields from times when their cores were still active. There is an understated irony in the way these anomalies, born of local irregularities, preserve information about processes far larger than themselves. A basalt flow on the seafloor captures not only the direction of the field as it cooled, but also becomes part of a global reversal sequence. A magnetized suture in the crust preserves the record of a vanished ocean not through fossils or sediment, but through alignment. A pale magnetic grain buried in desert soil may preserve the direction of a pole that no longer exists, oriented toward a magnetic north, now thousands of kilometers away. These are not monuments built to last, but incidental records, traces left by the interaction between molten metal and cooling rock, between planetary flow and surface stillness. In some places, magnetic anomalies are so pronounced that compasses spin erratically, or point toward local features rather than the true magnetic north. In others, the variation is so subtle it requires sensitive instrumentation to detect. There are no visible signs of these anomalies, no colour, no texture, no shadow. They exist only in measurement, in deviation, in the gentle tug of a field that does not behave as expected. Their silence is complete, but their presence is not passive. They shape how we measure, how we navigate, how we interpret the past, and in doing so they reveal the magnetic field not as a single, unified entity, but as a layered, shifting fabric woven through every part of the Earth. Even the notion of a single magnetic pole becomes complicated in light of these anomalies. While the geomagnetic poles define the general direction of the field, localized regions may contain their own centers of flux, creating magnetic microclimates, where the field behaves differently than global models predict. This is especially true during reversals or excursions when the dipole weakens and the field becomes multipolar. In these moments, the field structure becomes more chaotic, and anomalies play a larger role in shaping how it manifests at the surface. What was once a simple system of north and south becomes a tangled web of magnetic islands and diffuse gradients. The field does not disappear, it fragments, and in doing so reveals its underlying complexity. There is also a quiet beauty in this fragmentation. The field, though generated by a single dynamo, does not demand uniformity. It accommodates variation, local expression, geological memory. It flows through regions shaped by ancient volcanoes, subduction zones, mineral belts and tectonic scars. It wraps itself around mountain ranges and ocean basins, responding not just to the convective currents of the core, but to the crust it passes through. The field in this way becomes an interpreter, translating the deep, chaotic language of the outer core into the local dialects of the continents and seas. Still, for all their usefulness, anomalies are reminders of what we do not fully understand. They hint at hidden structures beneath the crust, at processes beneath the mantle, at shifts in the dynamo that leave partial marks on the surface. They are incomplete messages from a deeper realm, like echoes from a moving object we cannot see. Each anomaly asks a question: what happened here, and why each one offers a clue, but never a full explanation. So the magnetic field continues to flow, to distort, to leave behind these irregular signatures. Satellites chart their outlines, aircraft trace their contours, scientists publish their maps. And all the while the field changes. New anomalies may form, old ones may fade. The dance between motion and memory continues, hidden beneath forest canopies, frozen into polar ice buried beneath the seafloor. It does not end, it only shifts. The magnetic field, though born of deep planetary motion, does not always hold steady in its direction or form. Sometimes, instead of fully reversing, it enters a strange ephemeral state, what scientists call a magnetic excursion. These events are not true reversals where the field's polarity flips entirely and settles into a new orientation, but rather brief partial disruptions in which the field weakens dramatically, and the poles wander far from their usual positions before returning. They are deviations, moments of magnetic instability in an otherwise persistent cycle. Unlike full reversals, which may take thousands of years and leave a clear imprint in rocks and seafloor patterns, excursions are harder to detect. Their signatures are often subtle, patchy and localized, and their global effects remain poorly understood. Yet their occurrence reveals that the geodynamo is capable not only of polarity flips, but also of sudden, unpredictable wanderings, episodes of almost reversal that never quite complete. One of the best-known excursions is the Lachon event, which occurred around 41,000 years ago during the last glacial period. Evidence from volcanic rocks in France Lake, sediments in Asia, and ice cores from Greenland suggests that during this time the magnetic field strength dropped to a fraction of its current level, perhaps only 5% to 10%, and that the poles drifted to unexpected latitudes. In some reconstructions, the North Magnetic Pole approached the equator. For several hundred years, the field's shielding effect was greatly diminished, allowing more cosmic and solar radiation to reach the Earth. Then, as suddenly as it began, the excursion ended. The field recovered, realigned, and resumed its familiar dipolar configuration. No mass extinction followed. No catastrophic climatic upheaval is firmly tied to the event, and yet its traces remain embedded in the isotopic composition of ice cores and the magnetic signature of ancient sediments. It was a whisper of chaos in a system that often seems so stable. Other excursions have been identified, though, with less certainty. The Mono Lake event, the Blake event, the BYY and 2 excursions. Each shares the same ambiguous nature, a sharp decline in field strength, an erratic pole migration, a short-lived period of instability, and an eventual return to the status quo. Their timing, frequency, and global impact remain matters of debate. Some researchers argue that excursions are more common than previously thought, but their incomplete or localized magnetic imprints make them hard to distinguish from other forms of secular variation. Others question whether some identified excursions are real at all or artifacts of remagnetization, sampling error, or interpretive bias. The deeper the excursion lies in time, the fainter its signal, and the more difficult its confirmation becomes. The mystery lies not only in their detection but in their origin. What causes the field to falter, to fragment, to drift into such irregular configurations? If reversals are expressions of fundamental instabilities in the geodynamo, are excursions simply failed? Reversals attempts at polarity change that never fully succeed? Or are they a distinct phenomenon driven by short-term imbalances in convection, transient shifts in heat flow, or fluctuations in core mantle interactions? Some numerical simulations of the geodynamo suggest that even small perturbations in flow patterns can produce field weakening and multipolar behavior, especially near the threshold of stability. These simulations reproduce excursions without external triggers, implying that the system itself, chaotic and nonlinear, may naturally drift into such states. But the precise conditions that favor excursions over full reversals remain elusive. It is a system of internal thresholds sensitive to changes we cannot observe directly. There is an irony here. We often imagine the magnetic field as a reliable compass, a stable guide, a planetary constant, and yet excursions remind us that it is nothing of the sort. It can fade, shift, divide, and reform all without external cause, all while remaining invisible to the untrained eye. For those alive during the Lachamp event, the sky may have looked no different. The stars rose and set. The seasons turned. Yet above them and around them, the field flickered, weakened and reoriented, allowing cosmic radiation to seep further into the atmosphere. Isotope records suggest increased production of beryllium-10 and carbon-14 during the event, chemical echoes of a world briefly more exposed to space. Some have speculated that these changes may have affected human evolution, or the distribution of flora and fauna, or even the development of symbolic behavior, but the evidence is tenuous and the connections remain speculative. What excursions do confirm is that the magnetic field is not a passive byproduct, but a living system, dynamic, reactive, and susceptible to sudden change. It exists in a delicate balance between flow and force, between heat and structure. The fact that it can fall out of alignment without collapsing entirely suggests resilience, but also instability. It does not break. It wavers, it does not vanish, it dims, and in doing so it offers a rare glimpse into the boundary between order and chaos within the deep earth. Excursions also challenge the idea of reversals as binary events. The field does not simply flip from north to south. It transitions, fragments, drifts. The path is winding, the outcome uncertain. Sometimes the transition completes, sometimes it reverses its reversal. In this ambiguity lies the field's most elusive characteristic, its unpredictability. We can model its general tendencies, measure its present state, and trace its past behavior, but we cannot yet forecast its future with certainty. Will the South Atlantic anomaly deepen into a new reversal? Will another Lechamp-like event occur within a few centuries? Our simulations offer scenarios, not answers. Still, the field holds. Even in its weakest moments, it continues to structure the near-Earth environment, guiding charged particles, shaping the magnetosphere, supporting navigation, and preserving the habitability of the surface. During excursions, satellites may suffer more radiation, auroras may spread further from the poles, and atmospheric chemistry may shift. But the field never truly vanishes. It retracts, it ripples, but it remains. That resilience, quiet and uncelebrated, is part of its character. It is not a shield of steel, but of motion, a flickering veil drawn from planetary flow. So the Earth turns and the core churns, and the field in its quiet complexity lives between reversal and restoration. Excursions come and go like skipped beats in a deep ancient rhythm. We study them, name them, trace their isotopic echoes, but we do not control them. We only wait. Not all magnetic reversals unfold at the same pace. Some take tens of thousands of years to complete a slow, meandering process during which the field weakens fragments and then gradually reorients in the opposite direction. Others seem to move with surprising speed, flipping within a few centuries or even less. This variation in reversal speed is one of the magnetic field's more puzzling behaviors, hinting at complexities within the geodynamo that are still not fully understood. If the underlying mechanism, convection in the liquid outer core, follows the same physical laws everywhere, then why should some reversals linger and others rush? Why does the field hesitate during some transitions and proceed decisively through others? The answers remain elusive, hidden in the turbulent interplay of heat, motion, and symmetry deep beneath our feet. We infer the duration of reversals primarily from sedimentary sequences and volcanic flows, each offering different resolutions. Sediments accumulate slowly, layer by layer, preserving faint traces of the geomagnetic field's orientation in the alignment of magnetic particles as they settle. Volcanic rocks, on the other hand, lock in their magnetic direction instantly upon cooling. By sampling a sequence of lava flows erupted during a reversal, scientists can reconstruct how the field evolved over time. In some cases, these records show a drawn-out transition with partial field collapse and multipolar phases lasting thousands of years. In others, they suggest an almost abrupt shift with the dipole reversing in the time between two closely spaced flows. The discrepancy may reflect differences in resolution, or it may point to genuine variability in reversal dynamics. One hypothesis is that reversal speed depends on the symmetry or lack thereof within the core's convective patterns. If the flow becomes highly asymmetric, or if certain key structures destabilize quickly, the dipole may flip rapidly. Conversely, if the field transitions through a more complex multipolar state, it may take longer for a dominant polarity to re-emerge. Simulations of the geodynamo support both possibilities, producing reversals that range from sharp to sluggish, depending on initial conditions. But models, no matter how sophisticated, remain simplifications. They operate at higher viscosities, lower Reynolds numbers, and coarser spatial scales than the real Earth. They offer insight, not certainty. There is a quiet irony in the fact that the planet's magnetic identity, its north and south, its invisible alignment with space, can change with such inconsistency. In some epochs, the field flips frequently. In others, it holds its orientation for tens of millions of years, And when it does reverse, the process may take a geologic breath or a cosmic blink. From the outside, there are few visible signs. The rocks remember, but the surface does not notice. It is only by looking backward through the imprints in stone that we discover how transient the concept of magnetic north truly is. This variability in reversal speed raises important questions for the present. Today the field is weakening, particularly over the South Atlantic, where an anomaly has grown in extent and intensity over recent decades. Some have wondered whether we are entering the early phase of a new reversal or excursion. If so, how fast might it proceed? Could the field flip within a human lifetime or even a single generation? If that occurred, what would the consequences be? Would the magnetosphere collapse, entirely exposing Earth to a dangerous flux of radiation? Would satellites fail, power grids falter, species lose their navigational cues, or would the transition unfold so slowly and unevenly that the biosphere and technology could adapt? The truth is no one knows. Past reversals leave no trace of global catastrophe. Life endured, diversified, evolved. There is no mass extinction that aligns cleanly with a magnetic reversal, and yet our world is not the same as it was. We rely on magnetic navigation systems on satellites vulnerable to radiation, on high-altitude flights and deep space missions. The biological world might survive a reversal unchanged. The technological world might not. But whether the next reversal arrives in 1,000 years or 100, whether it comes gradually or swiftly, it will come as it always has, without warning, without pattern, without pause. The field, after all, does not explain itself. It gives no signal of its intent, no forecast of its future. It simply changes according to principles buried in the chaotic mathematics of fluid motion under planetary rotation. Each reversal is a unique solution to a set of ever-shifting conditions. The Earth turns the core flows and the magnetic field responds not as a ruler but as a consequence. It is not the driver of change but its expression. Still, the possibility of rapid reversal unsettles the idea of planetary permanence. We imagine Earth's magnetic poles as fixed, its dipole as stable, its compass as reliable. But history tells a different story of reversals that arrive without rhythm, that take thousands of years or perhaps only centuries, that transform the field, not once, but many times. And in each case the planet continues indifferent to its own transformations. The field does not define the Earth, it reflects it. This indifference may be the field's most haunting quality. It does not favour life nor seek to preserve it. It does not align itself for our benefit. Its stability is temporary. Its reversals are neither good nor bad. They are part of the deep, slow machinery of a planet still cooling, still rotating, still convecting in darkness. What changes is not the field's purpose. There is none but our perspective. We see in its shifts a kind of narrative, a drama. But the field offers only motion, so we watch. We monitor the strength and direction of the field from satellites and ground stations. We simulate its behaviour in vast digital cores. We drill into lava flows and read the rock as one might read a forgotten language. We try to understand what makes the field move quickly and what slows it down. But the answers are always partial, always shaped by limits of resolution, by noise in the data, by the impossibility of reaching the core. The field moves on. It has done so for billions of years. One day, perhaps soon, it will reverse again, or it will not. It will pause, weaken, fragment, reform. It may reverse quickly. It may not. The poles may migrate thousands of kilometers or shift only slightly. The dipole may decay entirely for a time, or it may stabilize without warning. The timeline is unknown. The process is not inevitable, only probable. The field, like the planet, continues on its own terms. Elsewhere in the solar system, beyond the blue curve of Earth's horizon and the reach of its own magnetic veil, other planets tell fragments of the magnetic story from different perspectives, some with silence, others with echoes. Mars, once geologically active, and perhaps once magnetic, now stands exposed beneath a thin, fragile atmosphere. Ancient crustal rocks on Mars retain strong localized magnetization locked in before the global dynamo faded. These remnants preserved in the southern highlands suggest that Mars once had a magnetic field generated by a core dynamo much like Earth's today. But at some point, perhaps more than 4 billion years ago, the Martian field disappeared. The convective engine powering its geodynamo slowed, weakened and stopped. Without a shield, solar wind stripped away much of the Martian atmosphere, and the planet that may once have supported rivers, lakes and a thicker sky was left barren and dry. The loss of magnetism did not cause this transformation alone, but it accelerated its finality, making Mars a quiet record of what a world can become when its field goes still. The Moon too offers a magnetic puzzle. Though airless and geologically quiet now, its ancient basalts contain signs of a long-extinct field, strong enough in some periods to rival or exceed Earth's current magnetism. These magnetized rocks returned by the Apollo missions were unexpected. The Moon's core is small and mostly solid, making a sustained dynamo unlikely. Yet evidence suggests that for hundreds of millions of years some form of lunar dynamo existed. Whether it was powered by core crystallization, mechanical stirring from Earth's tidal pull, or some other still unknown mechanism remains unresolved. What is clear is that the Moon once had a field, and now it does not. It carries a silent archive of this transition in its soil in glass beads, melted by micrometeorites in the faint alignment of tiny magnetic grains, cooled during ancient eruptions. It is a graveyard of magnetism, and yet it speaks. These planetary comparisons are not just exercises in curiosity, they illuminate what makes Earth's field both rare and resilient. Mercury has a weak but persistent magnetic field, perhaps sustained by partial core convection in a highly iron-rich planet. Jupiter and Saturn gas giants with deep metallic hydrogen layers generate enormous and complex magnetic fields, their strength and extent dwarfing Earth's. Uranus and Neptune offer even stranger geometries with off-center tilted fields that vary dramatically across their surfaces. Yet among all these, Earth's field remains unique in its role, not just a generator of magnetospheres, but a key player in maintaining surface conditions suitable for life. Only here does a solid surface active geology liquid water a substantial atmosphere and a long-lived magnetic field coincide. The field does not cause life, but it preserves the delicate balances in which life persists. And yet despite this protective presence, Earth's field is fragile. It weakens, it wanders, it reverses, it grows anomalies and fades at the edges. It exists because of conditions that may not last forever: a convecting outer core, a cooling inner core, a still rotating planet. One day, far into the future, the dynamo may slow, the core may crystallize entirely, the flows may cease, and with them the magnetic field will vanish. This will not be sudden or cataclysmic. It will unfold over millions of years quietly as the internal gradients flatten and the motion still. The field will ripple into nothing, and the Earth will again face the solar wind without armor. That day is not near, but the Moon and Mars remind us it is possible. Fields can vanish, magnetospheres can fade. The solar system is old, and not all of its stories end with persistence. Earth's field is not permanent. It is like so much else a phase. That it has endured this long is not destiny but fortune, an outcome of heat, pressure, rotation and time. We live beneath a sky structured by that fortune, but the deeper processes remain indifferent to its consequences. There is a quiet elegance in how other worlds preserve the memory of their lost fields. No record remains in their skies, no compass swings on Mars, no aurora dances on the moon, but the rocks remember. In them the ancient alignments persist frozen in place. These planetary archives offer contrast: Earth, magnetic and alive, others still and mute. In this comparison lies not judgment but reflection. The conditions for a magnetic field are precise, and the persistence of that field is even more delicate. It requires the right composition, the right thermal history, the right rotation rate. A small shift in any parameter and the field falters. Back on Earth, we measure these planetary legacies with orbiters and landers, with magnetometers and spectrometers. We build models of early Mars, of lunar dynamo scenarios of Mercury's sluggish core. And through these reconstructions, we gain perspective not just on other worlds but on our own. The presence of Earth's magnetic field is not an inevitability. It is a particular outcome of planetary evolution, one that could have turned out otherwise. That it did not makes it no less vulnerable. Still, for now, the field remains. It hums with energy, flows with motion, and reaches into space. It guides birds across continents, shields astronauts aboard satellites, and carves invisible paths for charged particles above the poles. It ripples in auroras and flickers in storm-battered ionospheres, and beneath it all the molten core moves, iron flows, heat rises, crystals form, the dynamo endures. From other worlds we see what is lost, from Earth we feel what remains. The contrast is instructive. Magnetism is not only a force, it is a memory, a record of movement, of transition, of deep time expressed through alignment. When the field one day fades, Earth will not be silent. The crust will still bear its story, etched in basalt and sediment, told by rocks that remember where North once lay. In this Earth will join the others, not diminished, only changed. The field will have passed, but the memory will persist. Today, Earth's magnetic field remains active, but signs of its slow evolution are everywhere. Measurements from satellites, oceanic instruments, and land-based observatories reveal that the dipole strength has declined by nearly 10% over the past century, a blink in geological time. Most notably, the South Atlantic anomaly continues to grow, stretching across continents and lowering the field's intensity in a region now large enough to disrupt satellites and expose orbiting instruments to higher radiation levels. The question arises with increasing frequency: are we witnessing the early stages of a reversal and excursion, or merely a transient weakening? The data-rich and continuous offer no clear answer. The field as always changes on its own terms, revealing patterns only after the fact. We are observers, not participants, and the field is not a performance. Our most detailed understanding of the present field comes from satellites such as ESA's Swarm Constellation 3 spacecraft orbiting in formation, continuously mapping the magnetic environment of Earth. From their measurements, we detect not only the slow drift of the magnetic poles, but also fine-grained structures in the field, regional patches of stronger or weaker intensity, subtle shifts in the direction of the field lines, variations in the crustal magnetism that overlay the deeper geodynamo signals. These modern tools allow scientists to isolate the different sources of the field: the dominant core field generated by the outer core, the lithospheric field from magnetized rocks in the crust, the ionospheric field induced by solar radiation, and the magnetospheric field shaped by space weather. Each component interacts with the others, forming a superposition of magnetic effects that we untangle only through careful modeling. One striking realization from this global monitoring is how dynamic the field truly is even over short timescales. Annual changes in direction known as secular variation are now mapped in detail. In some regions, these variations are smooth and steady. In others, they show abrupt shifts known as geomagnetic jerks, sudden changes in the acceleration of the field's motion that may reflect alterations in core flow patterns. These jerks are not well understood. They occur regularly with no apparent external cause, and their signals ripple through the magnetic field like pulses from the deep. Their detection marks yet another layer of complexity. Not only is the field changing, but the rate at which it changes also varies in patterns that do not follow obvious cycles. This irregularity has implications not just for science but for society. The global magnetic field underpins much of our modern infrastructure. Aircraft rely on magnetic headings. Surveyors and drillers use magnetic orientation. Navigation systems, particularly in remote regions, still depend on models that predict field behavior. The World Magnetic Model, updated every 5 years, integrates data from satellites and observatories to offer the best available representation of the field for practical use. But the field's unpredictability makes this task challenging. The most recent update was issued ahead of schedule as the North Magnetic Pole accelerated towards Siberia faster than anticipated. It is a reminder that even as we map the field with precision, we cannot fully anticipate its next move, and so we adjust. Magnetic declination. The difference between magnetic north and true north must be recalculated regularly. Engineering systems are built with tolerances that assume fluctuations. Satellites are hardened against radiation exposure. Manned space missions account for magnetic anomalies in orbital planning. Yet behind these technical responses lies a deeper truth: the field is not a fixed backdrop but a living system, and we, for all our instruments and simulations, live within its changing contours. There is an irony in the way we treat the field as both a constant and a variable. It structures our models of Earth, shapes our understanding of the planet's interior, and grounds our orientation in space. And yet we know it is temporary, ever-changing, a veil drawn from the churning of fluids we can never reach. It is reliable, but not permanent, predictable, but not entirely understood. We build our expectations around its behavior, while knowing that it has reversed, weakened, and vanished before and will again. The stability we experience is momentary, a pause in a longer story. The modern field also offers a rare chance to observe the geodynamo in action, to capture changes in real time, to refine our models as the data flow in. With each new measurement, each new observation of secular variation or core flow, we gain a slightly clearer picture of the processes occurring thousands of kilometers beneath our feet. It is a slow revelation, one formed not in headlines but in data sets, not in sudden discoveries, but in decades of accumulation. And in this patient effort we find the essence of studying the magnetic field, not to control it, not to master it, but to learn how to listen. What we hear through instruments and calculations is a field in motion, a field that responds to heat, from the inner core to chemical composition in the outer core to the rotational forces that shape the entire planet. It is a system defined by flow, by boundaries that slip and curve, by feedbacks that are subtle and non-linear. No part of it stands still and no part of it speaks clearly. But together these motions compose a planetary hum, a deep quiet rhythm that marks the turning of the Earth, not in days but in millennia. And so even now the field continues to evolve. It weakens in some places, strengthens in others. Its poles wander, its anomalies grow, its orientation tilts. These are not signs of catastrophe, but of continuity, reminders that the field, like the planet, lives in cycles far older and broader than human perspective. We are here in a moment of flux, measuring, adjusting, wondering. The compass needle still points, but it drifts. The field still shields, but it breathes. In this living field we find not stability but presence, a presence that is never quite the same, never fully known, but always there, moving through rock, through sky, through space. It is not a relic, it is a process, and we briefly live within its changing shape. Beneath all change, behind all motion, Earth's magnetic field remains an expression of the planet's deep interior, a quiet surface echo of molten rivers far below. It is easy to think of magnetism as abstraction, as invisible influence, yet it is rooted in something very real, the chaotic convecting currents of liquid iron in the outer core, moving in spirals shaped by heat buoyancy and planetary spin. The field arises not from intention or design, but from the complex geometry of motion. It is an emergent force, a pattern born of turbulence sustained not by structure but by process. Every reversal, every excursion, every wandering pole is a natural consequence of this ongoing churning, a byproduct of how the Earth loses heat and balances its internal gradients. The field is not constant, but it is persistent. It has existed for billions of years, changed its shape and direction many times, and still it continues unseen, essential, alive. Its persistence is perhaps its most haunting quality. The field does not seek survival, yet it survives. It is shaped by no will, yet it shapes so much. In the grand scale of planetary systems, magnetic fields are not rare, but long-lived stable fields like Earth's are. Many planets have lost theirs, some never formed them. Earth's is the outcome of a narrow set of conditions, a molten metallic core that remains convecting, a cooling rate that sustains flow, a solid inner core growing slowly at the centre. Disrupt any one of these and the field would weaken, then vanish. That it has not done so for billions of years is not destiny, it is coincidence layered over thermal history, chemical evolution and rotational persistence. In this, the field reflects the Earth itself, shaped by accident, refined by time, and sustained through quiet motion. That motion cannot be seen, but it can be felt. It leaves traces across the seafloor locked in the magnetization of ancient basalts. It whispers in the orientation of crystals formed in magma chambers long extinct. It pulses in satellite data in auroral curtains, shifting with solar wind, in the alignment of migratory birds that follow geomagnetic cues across oceans. The field touches every layer of the Earth from the deepest liquid core to the frozen ice caps, yet it remains elusive. It wraps around the planet as a shield, yet bends under pressure. It seems permanent, but its past proves otherwise, and in the quiet spaces between those changes lies a pattern too vast for a single life to witness. The magnetic field does not move to the rhythm of seasons or centuries. It operates in the silence of geological time. It changes invisibly at first, then unmistakably. Reversals occur without ceremony. Anomalies grow without warning. Pole drift accelerates, then slows. There is no signal to the creatures living under its veil, no sound, no flash, no rupture, only slow transformation that leaves its evidence in minerals and models. We try to understand it, but we do so from the surface separated by thousands of kilometers of solid and molten rock. We study it from the outside, drilling into rocks that remember watching for auroras that dance along its invisible paths, building simulations that try to match its flow. Our models are approximations, useful, intricate, but always incomplete. No machine can yet capture the scale and complexity of the geodynamo. The equations are known, but the system is too vast to simulate in full. And so we live in a world shaped by a process we can describe but not predict, a field we can measure but not fully explain. Still, the attempt is worth making. In the field's changes, we glimpse the living Earth not as static sphere, but as a layered, turning body with a molten heart. every shift in magnetic direction, every drop in field strength, every ripple in satellite data reminds us that our planet is not finished. It is not fixed. It is still in motion. The inner core grows grain by grain. The outer core churns in complex spirals. The crust records each transition in silence. Together these processes maintain the field of veil that deflects solar wind guides, animal migrations, preserves atmospheric integrity, and quietly allows the surface to thrive. There is irony in how essential the field is and how recently it was discovered. For most of human history its presence was unknown. Compasses revealed its direction but not its origin. Only in the past 2 centuries have we begun to trace its source, to piece together its behavior over time, to measure its strength and shape and drift. And yet the field has been here far longer than we have. It shielded the earth before life began. It survived the bombardments of the Hadean, the oxygenation of the Proterozoic, the splitting of supercontinents, the rise and fall of empires. It is not for us, and it does not answer to us. It exists because the core moves. That is enough. And so the field continues for now, weakening here, strengthening there, the poles drifting slowly across hemispheres, the anomalies growing, contracting, uncertain. We do not know if a reversal is beginning, or whether this is simply another moment of quiet fluctuation. The data point both ways. The field has no need to resolve our questions. It will do as it has always done, turn, shift, linger, vanish, return. Perhaps in 1,000 years it will be entirely different. Perhaps not. What remains is the pattern, the slow breath of molten metal, the emergence of invisible lines, the formation of a shield that holds without sound. It is the rhythm of a planet cooling from the inside out of convection, turned to structure of energy made into direction. The magnetic field is not a story in the usual sense. It has no hero, no climax, no conclusion. It is process-made, manifest, ongoing, indifferent, essential. And we for a brief time are witnesses. Now the movement slows. The iron flow beneath settles into a quieter rhythm, imperceptible but enduring. The poles drift on unseen far above forests, cities and ocean tides. There is no final moment, no end to this unfolding. The magnetic field continues not as a destination, but as a presence invisible yet intimate, stretching from the deep core through the stone crust, through the sky and out into space. It is not still yet, it brings a kind of stillness. It does not speak yet. It has spoken across billions of years in the alignment of crystals, the paths of birds, the flicker of auroras in polar night. There is comfort in this slowness, in this vast unseen shield that asks for nothing, explains nothing, and yet holds so much. Beneath it the earth breathes, the core turns, the silence lengthens. Let it continue as it always has. Let the planet sleep beneath its own magnetic veil.